let's get started. So today I'm very happy to introduce our speaker, Dr. Rahul Hadi. And Rahul is an assistant professor in the EC department at University of California at San Diego. And he received his PhD from the University of Wisconsin, Madison in 2022 under the supervision of Professor Rob Novak. And there's a small personal connection. So Rob is the advisor of my postdoc mentor at Arizona State. And then after his PhD, Rahul went to EPFL for a postdoc for a couple of years. So his research focuses on the mathematical foundations of neural networks with connections to functional and harmonic analysis and approximation theory and statistics. I think some of you might have attended his excellent tutorial on function-space tour of data science. And I think the slides are also available on the website. So if you want, you can ask somebody to share the link. On the personal note, what I really like is clarity of exposition and the aesthetics of the slides. That's something we can all learn. So Rahul, take it away, present your beautiful answers.
Okay, yeah, thank you so much for the introduction. So today we're going to talk about what kinds of functions do neural networks learn, and we'll look at two different kinds of solutions you might hope for when you're actually training a neural network, which I'm calling low norm and flat solutions. So I'll define all of this as we go. So just to get started, I just want to mention this is joint work with Tong, Yuxiang, and Alex. In particular, Tong is a very bright PhD student who did all of the hard work that I'm going to present today. So as everyone here probably knows, the world is now based on neural networks. Large language models like GPT have taken the world by storm. Gemini 3 came out a couple months ago and it was beating all of the benchmarks. But at the same time, some people are saying things like, large language models will never actually be intelligent. So, I guess based on that, an important question to ask is, do we even understand, why or how do neural networks work? Today, we won't talk about large models or language models because we want to prove theorems. But for simple neural network models, we'll see some very sharp results that we can actually derive. In particular, the focus of this talk is going to circle around this idea of understanding generalization in neural networks. And some people might say that understanding generalization is really one of the principal outstanding problems in deep learning or AI research. So there's many questions related to understanding generalization. So there's things like what role does regularization play in the problem? What role does the training algorithm play in the problem? Because you're doing some kind of optimization procedure to actually train your neural network. Then you can ask questions like, what role does the geometry of the loss landscape play? Because neural network parameterizations are inherently non-convex. So I have this non-convex landscape. I have lots of local minima, global minima. Maybe I have different curvature in different parts of the landscape. Does the geometry of that also play some role in generalization? So what we're going to do today is basically circle around these three questions to see if we can gain any understanding about this idea. In particular, this will be the setup that we're focusing on. So we'll look at shallow ReLU neural networks. So these are neural networks with one hidden layer and ReLU activation functions. And then these are the two kinds of solutions that we'll actually focus on. So the first will be global minima, which I'm associating with low norm solutions, which will be neural networks trained with an explicit weight decay regularizer. And then the second sort of case study we'll look at are local minima, in particular those that if you sort of look at the loss landscape, they're flat in the sense that these are large basins. And in particular, the second case study is motivated by a lot of recent empirical work and some theoretical work about the minima that gradient descent can actually find when you're training. And there's some interesting work called the edge of stability, which I'll talk about later, that really makes this precise in some sense. So part one of the talk will be about low norm minima, and then part two will be about flat minima. Okay, so part one. So just to get started, let's introduce the mathematical formulation that we'll use throughout the talk. So our goal is to understand analytic properties of trained neural networks. So what even is a neural network? Well, people use diagrams like this to depict them, but these are nothing more than functions. So they have some input x and then some output f theta of x. Okay, what is a neural network actually? Well, it's something that looks like this. So I take my input, I apply some matrix to it. That's a linear operation. Then I apply sigma here, which is some nonlinear operation. So this is the nonlinearity in the neural network, and then I repeat that linear, nonlinear, linear, nonlinear procedure a bunch of times. The number of times I repeat that is the number of layers, which I'm denoting by L right here, and theta here is the parameter vector, just the collection of all of the weights. So that's all a neural network is. And now if you're training a neural network to fit data, it means, well, one, you have some data set of XY pairs. And then when someone says that they're training it, it just means they're looking at optimization problems that look something like this. So we're optimizing over parameter vectors theta. And we have two terms. We have the data fidelity and the regularization. So you can think of L here as the squared error loss to just keep something in mind. And this first term is just making sure that the function that we end up learning is close to the data we're trying to fit. And then the second term is basically making sure the function we learn isn't too wiggly. And this kind of L2 regularization on parameters vectors is just called weight decay in sort of the modern words. And the goal in some sense, or the perspective that we're taking, is we're interested in the functions that are realized by the neural network. So really interested in understanding, if someone hands us a solution theta hat to this problem, what is f sub theta hat? What properties does that function mapping actually have? Okay, so why do they call L2 regularization weight decay, even though it's a very sort of classical idea? It just goes back to some old work actually, actually even going back to 1988. But the place this name came from basically came from taking our optimization problem and writing down its gradient dynamics. So let's look at the gradient dynamics on the ith component of this parameter vector. I'm going to get an iteration that looks something like this. So eta here is the step size or the learning rate, if you want. If I rearrange the terms a little bit, I'll get something that looks like this. And this first part here is just the gradient descent update on the data fitting part of our objective. And then the second term here is a small constant, which is the step size times the regularization parameter lambda times the current iterate. So this is what people will call the weight decay, because you're kind of like decaying the weights at every iteration. So this is why people call this the weight decay objective, but it's just L2 regularization. Okay, so something interesting happens when you use L2 regularization in conjunction with the parameterization of a neural network, and we call this the neural balance phenomenon. Oh, so if I zoom into one neuron in some deep neural network architecture, so this could be any architecture you want, and I'm going to zoom into one of the ReLU neurons. This neuron has some set of input weights W and some set of output weights V. And this blue circle here is just the ReLU activation function. So what does this neuron actually do? Well, it has some input, Z. And if I sort of put it through this neuron, this is what's going to happen. I'm going to take Z, I'm going to weight it by W, and then I'll take the positive part. So that's just the ReLU activation function. And then I'll multiply that by the output weight vector V. So this is just the mathematical expression for a single ReLU neuron. And again, when we're training our neural network with weight decay, it just means we're adding this L2 penalty to the objective. So if we do this, it turns out if you take your neural network, again, any architecture you want, and let's say you train it with weight decay and pretend you can actually find a global minimizer, then the two norms of the input and output weights of each ReLU neuron must actually be balanced. So just writing this explicitly, the norm of W must equal the norm of V. So why is this happening? It's not actually a very complicated idea. It's just boiling down to the fact that the ReLU activation function is a homogeneous function. What does this mean? It means if I take our input weight W, I scale it up by some constant gamma, and I scale down the output weight V by the same constant, this implements the exact same function as if I didn't have the gamma scaling. So at a global minima, this is enough to guarantee that the weights must be balanced. And the proof is just, this one line optimization problem. So the thing to keep in mind is that I can put in these sort of scalings all over my neural network architecture. Because I'm not changing the implementation of the function, actually, the data fitting part of my loss doesn't change. So I'm asking a question, what's the smallest sum of squares of the weights that sort of, keeps the same implementation? So that's what's being captured by this problem here. So you can take the derivative with respect to gamma, set it equal to 0. You'll find this as the solution, plug it back in, and you'll see that this actually means that they're balanced. Furthermore, this also means that at a global minimizer, if we look at the sum of the squares of the weights, it's going to equal this product form of the weights. So this is like the equality condition in the AMGM inequality.
You're getting this max of cluster.
I don't.
When you write this proximal mapping, when you L2 now as a regularizer.
Okay. With an L1, yeah.
But you're not using the 2 norm square.
Oh, actually, okay. So if you did this with the squared, you'd get the same thing. That's a typo. Okay. Yeah, and you'll see the same thing happen. Yeah. But thanks for catching that. That's been a typo in many talks I've given now, and you're the first person to notice that. So that's good. Okay. But yeah, so one more comment is that this idea is actually quite old. It goes back to this very classical paper by Convergence in the 90s, and then it was rediscovered by Neishaber et al. In 2015, and then became a very popular trick when studying neural network optimization problems. The reason why this trick is interesting, is there a question? Oh yeah, okay. Oh, I see it. Yeah. Okay, you scared me for a second. Yeah. Oh, okay, nice. Okay, cool. Okay, so we have this one hidden layer neural network. So this is now a function that looks like this, and now I'm going to include biases because it just makes some other stuff cleaner. But the balancing phenomenon does still hold. So now theta is my collection of all the W's, V's, and B's. And now, if I look at my problem here of interest training, the neural network with weight decay, by this neural balance phenomenon, it's equivalent to penalizing, the sum of the products of the weights. And then because the ReLU is a homogeneous function, I can basically absorb the effect of the input weights W into the output weights V via this unit norm constraint here. Okay, so let's look at the regularizers that we actually got from this. So this is, the weight decay regularizer, or the L2 regularizer. This one has a name in the neural network world. This is called the path norm. And this one should be familiar to many people here. This is just a lasso. So this is a sparsity promoting regularizer. And if you think about it for a second, because the V is the output weight of a neuron, this is promoting sparsity at the level of the neurons in the neural network. So then you can ask, like, okay, maybe the solutions to these problems won't be balanced. Are they really equivalent optimization problems? The answer is yes. I can take any solution to the bottom 2 problems, just rebalance the weights, and you can show that that's going to be a solution to the top problem. So you can use these 3 problems interchangeably. They are equivalent optimization problems. So this reveals something cool, that if I'm doing L2 regularization on neural network parameters, because of this parameterization, the sort of factorized parameterization with homogeneous activation functions, it's implicitly promoting sparsity at the level of neurons in the neural network. Question?
What about the previous 2 slides requires this 1 layer only?
So in this talk, going forward, we're going to focus on one hidden layer neural networks. The previous slides hold for deep neural networks as a whole. You always have this balancing phenomenon. And if you wrote a sort of vanilla deep neural network with L layers with ReLU activation functions, you can write down similar regularizers where now you sort of sum over the neurons in each layer and get basically a group sparsity regularizer there. Yeah. But you can write it out. But for the rest of the talk, we'll focus on one hidden layer, so we're specializing it. Sorry? Yes. Is there a question, a follow-up question? So from here to here, this is because of this neural balance theorem. From here to here, it's because the ReLU is homogeneous. So I'm taking the effect of the input weights and absorbing them into the output weights because I've added this unit norm constraint here. And then to sort of go from these 2 back to the first one, I know that my weights have to be balanced. So you can show, and this takes a, maybe a small argument, that if you rebalance the weights, you'll always get a solution to the top problem for one of the 2 bottom problems. Yeah. Okay. So why is the path norm nice? Well, it makes it so that we can sort of think about things in terms of the functions for real. Actually, what do I mean by that? Let's consider this set here. So these are finite width neural networks, and I'll make a note as I'm letting the width, which is the number of neurons k here, be any natural number. You can show that the path norm actually is a valid norm on this space, but the space isn't really complete in any reasonable sense. So if you take its completion in the correct sense, you will get a Banach space, and it'll be a Banach space of functions that take the form that look like this. So this measure nu that we're integrating against is just playing the role of the output weights. And these spaces have a name. People call them variation spaces, among other things. And this formulation of studying neural networks is very classical. It goes back to some foundational work of Andrew Barron, which was then followed up by a lot of other people. Cool. So what really are these variation spaces? Well, I have some function f in this space. I know it has this integral representation. I know there's some norm. What actually is the norm? Well, because every function in the space is parameterized by a measure, it turns out the norm of a function in the space is just the total variation norm in the sense of measures of that nu that I'm integrating against in the integral representation. Functionally, what does this mean? It means if someone hands me one of these finite width shallow ReLU neural networks, and I want to compute the variation norm of it, it's just going to be the path norm. In particular, we have this isometric isomorphism between V and the space of measures, and this makes it so that we can actually study V because we just have to study M and then sort of pull things back through an appropriate question. Yeah, so here I've normalized W to be unit norm. Correct. So it's on the sphere cross R, so cylinder maybe, if you want. Yeah, that's a cylinder. Yeah. Cool. So the reason why this, genuinely is sort of a correct infinite dimensional perspective on finite with neural networks comes from the fact that you can actually prove a representer theorem for optimization problems over this space. So if someone hands us any data set of XY pairs and then some loss function, you can show that if you look at this optimization problem here over functions in the variation space, and I'm doing data fitting plus regularization, regularizer is now the norm in this Banach space, there always is a solution that you can write like this. So it's a finite with ReLU neural network, and in particular, the solutions are sparse in the sense that the number of neurons in the solution is bounded by the number of data that we're trying to fit. What does this really mean? It means if I take a neural network and it's wide enough, meaning that its width is at least the number of data I'm trying to fit, and I train it with weight decay and pretend I can find a global minimizer, then I know that that guy actually is a solution to this Banach space problem. So if you ask the question, like what kinds of functions do neural networks trained with weight decay learn? They learn functions that are regular precisely in the sense of this Banach space, which is a variation space. Yeah. So exactly. So the no. So there exists one with this representation. There could be ones where the measure actually has like a density. Yeah. But there's always at least one sparse solution. If you want the stronger version of the result, if L is convex, you can show that the extreme points of the solution set in the space of measures are the sparse ones with the sparsity bound. So then take convex combinations, possibly continuously many. So you could, a lot of the time, you do have solutions that genuinely have continuously many neurons, but we know the extreme points of the solutions that are always sparse. Yeah. So this really motivates the function space viewpoint for studying neural networks. And it's basically from this chain of equivalences. So here's my neural network where I'm trying to train with weight decay. This is equivalent to the path norm regularized problem, up to some over-parameterized assumption of width being at least the number of data. This is then equivalent to optimizing in the function space. And this correspondence allowing us to move the problem to function space makes it so we can bring in a lot of machinery developed in the context of like functional analysis and harmonic analysis to then understand what is going on to the neural network solutions to these kinds of problems. And this is why I think this perspective actually is very nice. And the representer theorem and this chain of equivalences really shows that you don't lose anything or even gain too much in some sense by moving to function space. Okay, so we're interested in understanding how well neural networks work, how well they generalize. So how are we actually going to quantify how well do statistical estimators perform? So today we'll focus on the sort of usual statistical learning setup. So we have XY pairs drawn IID from some distribution P. You don't know the distribution P. And a common quantity people define is what they call the population risk. So like I draw a new sample XY from the same distribution P, and I look at the expected error, and here we'll focus on this squared error from this new sample with respect to some predictor F. So R is a function of F. We can never compute this because we don't know P. But we do have a bunch of training data, so we can define the empirical version of it, which we'll call R hat n, which is just the 1 by n, then sum overall of the data that I have, and then yi minus f of xi squared. So if you want to measure the quality of an estimator, you really do want a good handle on R of f, but you can never compute R of f. We can compute this R hat n of f. So what people call generalization bounds in statistical learning theory correspond to bounding the generalization gap, which is just the difference between population risk and empirical risk as a function of the number of samples n that you actually have. So this is what people call generalization bounds, and this is what we will use to sort of look at how well statistical estimators perform for today's talk. One comment I'll make is that if you know your function lives in some model class F that embeds compactly into L infinity, say on some bounded domain omega, this almost becomes an exercise in empirical process theory once you actually determine the L infinity entropy numbers. I'm trivializing a little bit, but basically once you have entropy numbers, it's kind of like plugging this into your favorite textbook on empirical process theory. So really this reduces the problem to determining entropy numbers of the model class of interest. So let's see what this actually means for these variation spaces. To do this, a sort of nice first step that makes things a bit easier is to look at approximation theory with neural networks. So I guess maybe first comment I'll make is the variation space does embed compactly into L infinity. So the notion of L infinity entropy numbers are well defined. Next, you can show, given a function f in this space, there exists a finite width ReLU neural network with k neurons, such that you have this L infinity difference between the function you're trying to approximate and the neural network you're approximating. So I have k to the minus 1/2 minus 3 by 2d, which you can always upper bound by k to the minus 1. Question? So in part 1, we'll see they don't explode. In part 2, we'll see they do explode. So maybe let's wait. Yeah. Otherwise, I don't know how to derive the entropy numbers in a clean way. Yeah. It's basically a tool to let us derive the entropy numbers in an extremely clean way. Yeah. And the way you derive this approximation rate, again, goes back to fundamental work from Andrew Barron, and in particular, I do want to highlight this Matuszek paper in 1996. This was really the first paper to give us techniques to do L infinity approximation in particular. So with that, there's a nice inequality in approximation theory called Karl's inequality, which basically says if I have an approximation scheme that's reasonable in some sense, it'll immediately give us a bound on the metric entropy of the unit ball of a Banach space. So just to give some context to these exponents, if this one is minus alpha, this delta to the minus 2d over d plus 3 is minus 1 by alpha in the exponent. And of course, you can always upper bound this by delta to the minus 2. So the takeaway message from what's going on here is that approximation rates and metric entropies don't grow with the input dimension before this class of functions. So putting all of this together, we can actually derive a generalization bound for these sort of low norm neural network solutions. So let's suppose that we have some data of XY pairs drawn IID from some distribution P. I do need some mild assumption. So I will suppose that the support of this measure P is bounded. Then you can show with high probability any solution to this problem here satisfies this generalization bound right here. So this is, the weight decay objective. So these are weight decay trained neural networks, and I have this, dimension-free generalization. So maybe one thing you can take away from this slide is that the generalization gap decays at a rate that does not depend on the input dimension D. So maybe the statement you want to make is low norm, global minima, generalize well. But to the people paying attention, this isn't a very realistic setup, actually, because I had to have access to a global minimizer, to this non-convex problem. And maybe there's no hope I can even find one of these, and this result is only holding for the solutions to this optimization problem. So let's store this result in our mind, and let's see if we can, sort of weaken the setup of our, kind of finding our neural network estimators to ones that are more, close to practice, and see if something different happens. Question. I guess you can find results that imply this result going back to at least 2015. Not written in this exact way, which is why I didn't cite anyone for this result. It's kind of like folklore or classical. People give it as a homework exercise in their statistical learning class, actually, via Rademacher complexity type arguments. But at least 2015, I know of references that will just imply this, for example. Okay. So again, store this result in your brain, n to the -1/2 dimension free, and let's see what happens if we try to make the setup closer to that of practice. So this will be part 2 of the talk, where we focus on local minima that are flat, which I will define shortly. So just to maybe give some motivation about this idea of actually looking at loss landscape geometry. So as I said at the beginning, is like these neural network parameterizations give you non-convex optimization problems. We have many critical points, local minima, global minima. We don't really understand the landscape in some sense. And then at the same time, when people train neural networks, they also don't explicitly regularize. So this weight decay penalty or this L2 penalty, oftentimes people don't even have that. And they're really relying on the implicit bias coming from this gradient-based procedure you're using to train neural networks. So there's a whole series of many hundreds or maybe even thousands of papers at this point trying to study the implicit bias of gradient-based training. And so this is really the optimization problem of interest. So again, f theta here's a one hidden layer neural network, and now least squares lost, and let's have no regularization. So this is really the problem of interest if you want to move a little bit closer to practice. So then you can start asking questions like, okay, what is the mechanism behind generalization in neural networks? There's many stationary points. Does the geometry of the landscape play a role in actually understanding what's going on? And to sort of make this explicit, let's maybe go on a short history detour back 30, is that 30 years ago? I guess that's about 30 years ago. There was this paper from Hochreiter and Schmidhuber in neural computation. This is the Schmidhuber you're thinking about. And basically the punchline of this paper is that if you look for minima that are flat, and I'll say what this means in a second, these kinds of minima are going to do better than anything else you would hope to do back in 1997, at least. So what is a flat minima? So I have this loss landscape. This is the theta landscape. A flat minima is a minima where the basin is very wide. And then you can say, okay, what's the opposite of flat? It's sharp. So a sharp minimum is one where the basin is very pointy. And the sort of heuristic argument they gave, and I think they even had some experiments in this paper, is that the minima that live in these kinds of basins are better than the minima that live in those kinds of basins. Okay, so this is 1997. There has been actually a lot of recent interest in this idea of looking at sharpness and flatness of the loss landscape in the last, maybe 10 years or so. So transporting ourselves 20 years forward from 1997, this is when sharpness-aware minimization came out. People here probably heard about it. It had a lot of hype. There's also this very cool paper called Understanding Generalization Through Visualizations. I like this paper in particular because, as the name suggests, it has nice visualizations. So I'll show you some of those right now. So here, this is a classification problem with the so-called Swiss roll data set. And the labels are basically red and blue. And these are two decision boundaries that were found by training a neural network. And these are both zero loss solutions, so they perfectly fit the training data. They perfectly predict red or blue on these training data points. This one intuitively looks like a much nicer decision boundary than this one. This one's all pointy and stuff, and maybe it's susceptible to adversarial perturbations, probably doesn't generalize well. What's nice about this paper is then they plotted the landscape, or at least a projection of the landscape, for both of these solutions. The one that intuitively looks nicer is like a flat minima, and the one that intuitively looks worse is a sharp minima. So this is the loss landscape. So they took like a low dimensional projection of the loss landscape so they could actually make a picture. So maybe one more comment I'll make. So, okay, so there's empirical evidence that the flat minima are also just good from the kinds of models that they learn. At the same time, if I'm running gradient descent, these are discrete iterations. If my step size is somewhat large, I might even jump over a sharp minima. Okay, so these things seem good from the kinds of models we learn. And at the same time, these are the ones that are actually likely to be found by gradient-based training. Okay. So now, theoretical insights are beginning to emerge to understand this phenomenon of, like, are flat minima actually good? So there's this cool paper in 2018 from Waina and U's group about how gradient-based optimizers actually sort of select solutions based on this idea of dynamical stability. So they looked at the gradient descent iteration as a dynamical system and actually said, like, okay, what solutions are sort of stable for this dynamical system, and related the stable solutions to notions of flatness or sharpness of the loss landscape. And in particular, what's interesting is this was the first paper to really characterize, like, okay, if I end up in a stable which will correspond to a flat solution, this actually tells me properties about the regularity of the function realized by the neural network. So this is sort of the perspective and the sort of work that motivated the stuff that we were doing that I'll talk about shortly. Okay, so which minima can gradient descent actually find? So again, just to remind everyone, the setup, one hidden layer neural network, least squares laws, no regularization. And we're doing gradient descent to train the model. So let's let theta be our parameter vector. And just remember, what is the gradient descent iteration? It's this guy here. Next iterate is current iterate minus step size times gradient of the loss at the current iterate. Okay. Gradient descent, fixed step size. This will be the setup we'll focus on. So for those of you who've taken an optimization class, there's this nice lemma called the descent lemma. And this is a reformulation of it that says that if the maximum eigenvalue of the Hessian of the thing I'm optimizing is upper bounded by 2 by eta, say, just for example, all points theta, then you actually always have descent in the sense that the loss of my my next iterate is less than the loss of my current. Okay, so this is interesting, and maybe it says that this inequality that the maximum eigenvalue of the Hessian is upper bounded by 2 by eta is fundamental in some sense. And this statement can actually be made precise through the lens of linear stability. So I'll tell you what linear stability is in a second, but essentially, if we think of gradient descent as a dynamical system and we look at the points that are linearly stable, these are precisely the ones that are going to be flat. And this is summarized in the following lemma. So first, what is linear stability? So let's say I have theta star, which is some minima, local minima, global minimum, whatever you want. And I put a quadratic approximation of my landscape at that minima. So I'm doing a second order Taylor expansion. And then I write down the gradient descent iterates for that quadratic approximation. If that dynamical system is stable in the classical sense, in the sense that the moment I enter a neighborhood of the minima, I'm trapped in that neighborhood, that's what linear stability is. So you can then show is that a minima is linearly stable if and only if the lambda max of the Hessian at that point is upper bounded by 2 by the step size. So why is this interesting? The maximum eigenvalue of the Hessian is precisely how you quantify the geometry or the sharpness of the loss landscape, and it's controlled by 2 over the step size. Question. Yeah, that's why I said informal here. Yeah. Okay, and I just want to make a remark is these are some nice papers that have looked at this lemma in the context of like neural network-like problems. And this last one here, which came out in JMLR last year, actually has a very nice, it was just written very nicely. So I'd recommend people check it out if they're interested in this idea of dynamical stability and flatness for overparameterized. So what does this lemma say? It says that larger step sizes are in some sense related to flatter minima. I mean, this implication is loose, just right now we're being a bit philosophical. But this lemma motivated us then to say, okay, let's look at parameters that satisfy this inequality, and then can we understand statistical performance of the parameters that live in this class? And if you want, I mean, these are precisely the solutions that gradient descent with step size eta can stably converge to. Clear? Okay, so before we then talk about how well do solutions in that class actually perform, I want to tell everyone about some recent empirical work in deep learning that also makes studying this class sort of very natural for neural network type problems. This is called the edge of stability phenomenon in gradient-based training. This is work that was sort of spearheaded by Jeremy Cohen, and these are 2 very nice papers about this idea. This last one has a lot of nice visualization, so I would maybe start there for anyone who's not familiar with this line of work. And what does this result say? It says if I'm looking at an optimization problem, it's non-convex, but it's non-convex in the way that neural networks are non-convex, and I do gradient descent training, fixed step size, full batch, I'm always going to see that the sharpness versus training epoch or iteration always has a curve that looks something like this. So at the beginning, I'm calling this intractable early stage because people see vastly different behavior sort of at the beginning of training. But then pretty much always there's this progressive sharpening phase and then this oscillation around some threshold. And this threshold is exactly 2 by the step size, 2 by eta. So this is this edge of stability phenomenon, is that you're sort of oscillating around the edge of stability in gradient-based training. So if you want to look at like gradient descent trajectories and you really want to study the ones that you sort of end up living in for a large portion of the training, studying this theta flat class is not too strange actually. In particular, studying this theta flat class does actually capture real gradient descent trajectories. There's almost no theory on this phenomenon actually. It's really surprising because of the fact that there's so much empirical evidence showing this curve. So if anyone's into dynamical systems, if you can prove that this happens in even like simple, say, matrix factorization problems, I think people would be very, very happy. I don't know. I don't know. I really don't know. Yeah. Again, this paper is nice. They have some heuristic reasons why it happens, but nothing super clean. So I don't want to say heuristic reasons. But I don't know. It's a good paper, so I'd recommend it. Yeah. So this is the sharpness. So it's the lambda max of the Hessian of the loss at, maybe I should have put theta t if you want. Yeah. Yes. Because it's a function. So sharpness versus iterate, if you want. Yeah.
Do we have any empirical evidence of how many flat minimizers?
I'm not actually sure, but I'm gonna guess that's just a hard problem in general. Yeah. Yes. This isn't discounting local minima. And the theta flat class never cared if you were even a critical point, actually. It only cared that the sharpness is less than or equal to 2 by eta. Yeah. Okay. So anyway, so this will be the setup that we work with. We're going to work with this theta flat regime. There's, sort of this theoretical connection with linear stability, and there's this empirical work about the edge of stability that motivated us to consider this class, basically. Yes? Like a perturbation of the parameter. Like if I'm in a flat basin and I move it, I'm not going to jump really far in the landscape. But if I was at like a very pointy place and I perturbed a little bit, I could jump somewhere kind of far. Yeah. Okay. So what is the implicit regularization coming from these stable or flat solutions? And what's interesting then is it actually imposes a data-dependent kind of regularization. So here's my one hidden layer neural network. What you can show is that if theta is in this theta flat class, this happens if and only if this inequality holds. I'm hiding a universal constant with the squiggle inequality. And if you stare at this for a second, this is just a weighted path. Norm, I'll tell you what the weight function g is in a second, but it does actually depend on the data that we're trying to fit. So this is a data-dependent kind of regularity. So what we can see from this inequality is that step size is implicitly controlling the regularity of the solutions. And people who know me know that I like function spaces. So this means that we can actually now play the same game we played before and lift the problem to function spaces so we can study the statistical performance of these estimators. So let's play the game we played before. We have this space here, a finite with neural networks. The weighted path norm is a valid norm on the space. So if I take its completion in an appropriate sense, I get this integral thing. Again, nu is the output weights. But what changes now is the norm on this function space now depends on the weight function g. Okay, so now we have the function space perspective of these theta flat solutions. What actually is this regularity? So this is what the g function looks like. At least upper and lower estimates make it so that it's equivalent to this quantity. It's very messy. So I have probabilities and expectations. The random variables drawn from the empirical law of the data we're trying to fit. So let's not dwell on this form too much, and let's look at an example because it'll clarify what's happening. So let's suppose my x's are drawn uniformly, and this is the unit Euclidean ball in RD. If my number of samples is sufficiently large, that empirical law will be pretty close to the population law. And from there, we were able to derive upper and lower estimates on the weight function g. And now, okay, w is unit norm, and b is a number. So this is like parameterized in, is that cylindrical coordinates, I guess. So just keep that in mind as well. But this g function looks like 1 minus size of b to the power d plus 2. D is input dimension. What does this mean for the functions that live in the VG space for the uniform distribution? So this weight function is decaying essentially quite quickly as we're approaching the boundary, which means a sort of prototypical function in this space might look something like this. It's very nice and smooth, strictly inside the domain. But as you get closer to the boundary, it could, in some sense, become arbitrarily irregular. So that's interesting. Another comment I'll make is you can show that VG actually does not compactly embed into L infinity. So this means that the metric entropy of the unit ball of the space is actually unbounded. So bounding the statistical performance actually is not a simple exercise in empirical process theory. Regardless, we found at least a way to do it. We had to develop some new proof techniques. Happy to chat offline for anyone curious. But we were able to actually derive generalization bound in this case. So what did we end up seeing? And this is where things become different from the low norm solutions. So let's suppose we have xy pairs coming IID from some distribution P. And now I'm going to put assumptions on the x marginal. So let's suppose that the x marginal is now uniform on the unit Euclidean ball. And again, let's just have the y marginal have the support be bounded. Then for n sufficiently large, you can show that with high probability, any solution that lives in this flat class is actually going to satisfy this bound right here. So we have n to the minus 1 by 2d plus 4. The d in the denominator of the exponent is precisely the curse of dimensionality. So then we asked, like, okay, maybe we were just really loose with math, and the fact that the space didn't compactly embed into L infinity meant that we had some stuff that was just super loose. Maybe we just messed up. So then we decided to derive a lower bound. This is a big mouthful to read, but basically, if I take the supremum over all of my parameters in my flat class, and then at the same time supremum over all distributions that satisfy this assumption, and then maybe the empirical risk estimator isn't a good choice of estimator, so let's also take the infimum over all risk estimators as well, we derive this lower bound right here, which is n to the minus 2 over d plus 1. So the upper and lower bounds don't match. This is related to our proof technique to derive the upper bounds, but at least what we see here is that the cursive dimensionality actually is necessary in this problem set. So maybe what we would then say is that flat minima generalize, but maybe they don't generalize well, because although this thing vanishes as n goes to infinity, it doesn't vanish, in a good way with respect to the input dimension. Okay, so this is kind of weird or interesting, because people are like, oh, neural networks work well, neural networks do everything better than any other method. I have 15 minutes. Okay, so maybe I'll just quickly go through this slide. So when you're driving lower bounds for like non-parametric statistics type problem, so it boils down to constructing a class of hard functions. So what are the hard functions for this type of problem? So this is a ReLU neuron. It has some activation threshold, which is the hyperplane W transpose X equals B. Because this weight function means that functions can be arbitrarily irregular as they approach the boundary, the functions that are hard are precisely the ones where this hyperplane cut essentially is being pushed towards the boundary. So this is how we constructed the hard functions for a lower bound, and then sort of did the usual Fano inequality sort of construction. The reason why this is interesting is for usual function spaces like Sobolev and Besov spaces, the construction for hard functions are like equally spaced bump functions. So this is actually a different kind of construction. So I thought that was just cool in and of itself for like proof technique reasons. But these hard functions also sort of clarify that neural networks that have their ReLU sort of near the boundary with high weight magnitudes are hard to learn. And because of the nature of the weight function, these have a very low norm in the Banach space, actually. In particular, the reason why we're getting this poor generalization performance is related to concentration phenomena in high dimensions. So, these are the hard functions in the problem. And, if X is uniform, that's the weight function. This is a nice homework exercise that also says that, if I have the uniform distribution in RD, or the unit ball of RD, and I crank D to infinity, all of the mass is going to start concentrating towards the boundary. And what this means is that, to have a cartoon picture in your head, actually pretend all the data points are at the boundary. I can use one ReLU neuron to basically then peel off a single data point with the hyperplane threshold, and then I can crank up the weight on that neuron to be whatever I want to actually interpolate the point. And this guy is going to have basically no norm in this VG Banach space because of the decay of this weight function. So this is maybe the cartoon reason why we're actually getting bad performance for these kinds of solutions, is precisely because ReLU boundaries are getting pushed. ReLU activation thresholds are getting pushed towards the boundary. Then we're like, okay, does this happen empirically? And it turns out the answer is yes. So maybe just to quickly say, what is this picture even showing? So we had a neural network, and we had some data. We generated the data by taking, I think it was like some low degree polynomial in like 8 dimensions, sampled it with some noise to get XY pairs. Then what I'm plotting here, so each dot is signifying one neuron, and then the y-axis, or sorry, the x-axis is signifying how many or what proportion of the x's actually live in the support of the neuron. So in the half space where the ReLU is positive. And blue is at initialization, and then on the left plot, red is after training where we don't have weight decay, and then orange in the second plot is after training where we do have weight decay. Y-axis is then the size of the weights of the neurons in the neural network. And then what we're seeing is actually when we don't have regularization, we train with gradient descent, fixed step size, this is actually showing that the ReLU neurons are being pushed towards the boundary because the number of data points in each of the activated regions is becoming very, very small. But the moment we have weight decay regularization, this effect becomes tame. So the hard functions from the lower bound actually end up being the ones that we end up learning. Okay, so what are some observations we can make? So what we saw is that ReLU neural networks are optimal solutions to data fitting problems in new function spaces. So these are these variation spaces and their weighted counterparts. We also saw that low norm solutions in flat minima are fundamentally different in the sense that they both generalize, but there's this sort of exponential separation with them where the flat minima seem to suffer the curse of dimensionality. So maybe what you want to say is that flatness isn't the sole explanation for generalization in neural networks. But then at the same time, you might ask, like, oh, okay, so the things that gradient descent actually find don't work that well. What's going on? And now this is where you can ask another question of a different kind of geometry, actually. Is like, does the data geometry itself actually play a role in what's going on? So here's a 2D function, and then I sample it, plus some noise to get XY pairs. But now my X's are supported on something low dimensional. It's a line. If I train my neural network with gradient descent, I actually end up picking up on the sort of low dimensional structure that was implicit in my data or in the function that generated the data. So what we're seeing from this empirical, small empirical experiment is that gradient descent trained neural networks are actually adapting to the intrinsic data geometry of the problem. And you can actually explain this via this weighted variation space perspective. So if you actually compute the G function for this distribution, if you learned a function that was tilted even a little bit, its norm in the VG space would actually blow up. So from this experiment, we're like, can we make this a quantitative statement? And I guess before we look at the quantitative statement, there's this idea of adaptivity in designing machine learning methods is we want them to be able to adapt to low dimensional structures that are sort of inherent in the data. So this is related to this idea of the manifold hypothesis. There's a lot of work on the subject, but maybe the punchline is that adaptivity to the intrinsic data geometry does matter for generalization. So here's the quantitative statement for this idea of having low dimensional data, actually. So I have XY pairs drawn IID from P, and now my PX distribution, I'm supposing, is basically a union of subspaces model. So I have a bunch of low dimensional disks, and I'm uniform on that disk, and I take the mixture of all of those disks. So let's say I take S subspaces, each of dimension R. Again, Py is bounded. Then you can show that if you find one of these flat solutions, your generalization bound looks something like this. So you see here, this is n to the -1 by 2r plus 4. So it's the intrinsic dimension rather than the ambient dimension. So what we're seeing then actually is that gradient descent trained neural networks actually adapt to the intrinsic structure of the data. So then you could ask then, like, oh, okay, are we always adapting to intrinsic dimension, or is there more of a geometric story to all of this? And it turns out this is true, and that the data geometry matters as well. So in this case, I'm supposing the X distribution is uniform on the sphere, so the boundary of the ball in SD. So SD -1. You could also work this out for SR -1, just change D with R. And what you end up finding, we're able to derive upper and lower bounds that show that you actually can't generalize. So the intrinsic dimension of the data isn't telling the full story, but something about the geometry or the curvature of the data manifold, if you want, is also part of the story. We don't have a complete explanation, but for these studies of union of subspaces and the sphere, we're seeing that curvature is doing something. Why do we get no generalization here? It's really coming back to this idea of the hard functions from our lower bound. So before, in the cartoon explanation I told you before for the uniform distribution, it's related to the fact that we're concentrating towards the boundary. Now I'm saying that the data points actually are on the boundary. So this idea that I can slice off a single data point and just interpolate it now is actually true in all dimensions. And that's why I can just straight up interpolate my data, and I don't get some kind of benign interpolation. I get some catastrophic overfitting, actually. And this is essentially the intuition why we get no generalization when the data is really on the sphere. So I guess with that, just to maybe summarize then, is what we see is even for shallow neural networks, the story of understanding generalization still isn't completely understood. So clearly, I mean, this is what we know now, I guess, is that the data geometry is playing a role. And this idea of adaptation to intrinsic geometry does happen, both empirically and theoretically. But we still don't know everything. But we do now have a platform to at least study this phenomenon with this new family of data-dependent Banach spaces, VG. There are now, of course, many natural open problems you could consider. So like, maybe like, is there some sort of intrinsic geometric way to think about this G function and the data manifold, of interest to sort of get a more unified perspective rather than working out case studies like union of subspaces or the sphere, like what we've already done. You can also ask, like, how architecture dependent is this theory? So everything I showed you today hinged on the fact that this was a one hidden layer neural network. We were explicitly using the parametric form of a one hidden layer neural network to even get anything that I told you. So you could ask, like, can I tell this story for other architectures and still get meaningful results? Then you can ask, like, what about other optimization methods? I talked about full batch gradient descent, fixed step size. But we don't even know what to do for like stochastic gradient descent, for example. And then step size schedulers are also a thing. How general are these phenomena and how tied are they to the optimization method is something else you could ask. But maybe the pessimist's perspective from all of this is that understanding generalization is confusing and we still don't really know what's going on. But if you want one maybe takeaway message from what I showed you today, is at least this idea of adaptation is there. And we actually are able to prove some nice theorems about that neural networks can at least adapt to intrinsic structure. So that's maybe a little bit satisfying because of the manifold hypothesis and this whole idea. But otherwise, I think that's a good place to stop. These last two papers are about part 2 of the talk. If anyone's interested, I would recommend checking them out. But otherwise, I'm happy to take any questions.